Superposition of electric forces. Electrical charges are attracted or repelled by all other charges around them. And actually, the force is an infinite force, but it gets really small pretty quickly because of that 1 over r squared term. Let's say we have a configuration consisting of multiple charges, like you have down here. 3 charges, Q1, Q2, and Q3. It is useful to calculate the net initial force on each charge. And I stress initial here, because this configuration is not going to stay static. Once you let them go, they're all going to move around, the equations will change, they'll be at different distances from each other, but we're not going to worry about that for now. We just want to find the initial net force on each charge. The simplest one is when we have all the charges in a line, for example, on the x-axis, like in this case here. We have a procedure for finding the net electric force. First, draw a free body diagram. Yep, we're never really done with free body diagrams, of the forces acting on each of the charges. Remember, like charges repel, opposite charges attract. Use Coulomb's law to find the magnitude of each force, and then use the free body diagrams to find the net force acting on each charge. And again, we're assuming that nothing moves. They stay where they are to find the initial forces. First step, draw a free body diagram of the forces acting on each charge. We're going to start with Q1 right here. Q1 is positive, so what's Q2? Q2 is this guy here. What's he going to do to Q1? He's going to attract him. So there'll be a force in this direction from Q2 on Q1. And we'll use a nomenclature here, force that 2 exerts on 1. Some books do it reverse, but these slides will do it this way. It's the force of 2 acting on 1. Now what is charge 3 trying to do to Q1? Well, they're both positive, so Q3, this guy over here, wants to repel Q1. So it'll have a force in that direction. That'll be the force of 3 on 1. And you can see here, a little bit neater with that one I just did. Don't worry too much about the lengths of the arrows. We're going to take care of that when we calculate the magnitudes. We're just interested in the directions here. Step 2. Use Coulomb's law to find the magnitude of each force. So let's first worry about the force that Q2 exerts on Q1. Okay. Using Coulomb's law, that's K Q1 Q2 over R12 squared. Again, not R12. That's the distance between charges 1 and 2. We call it R12. And then the force that Q3 exerts, which is the force of 3 on 1, is K Q1 Q3 over R13 squared. Finally, use the free body diagrams that we did in step 1, which you can barely see over there, and you'll find the net force acting on each charge. And we'll consider a force acting to the right as positive. That's pretty standard for what we do. And force going to the left will be negative. So in this case, here's our free body diagram for charge 1. The force that 2 exerts on 1 will be positive. You can see it there. And since the force that 3 exerts on 1 is to the left, we give that a negative sign. Summarizing our force labeling convention and also Newton's third law, F12, that's the force that Q1 exerts on Q2, and then so forth and so on. And you can apply Newton's third law, and the force that 1 exerts on 2 is equal to the negative of the force that 2 exerts on 1. Exact same magnitude, but the negative shows it's in the opposite direction.